So welcome everyone. Sorry for the delay in getting started. Welcome everyone to Climate Chat. I'm your host, Dan Miller. And today we have actually two special guests. This is great. We have Eliot Jacobson, famous as a climate doomer, but also famous as someone who presents lots of climate scientific data and posted on Twitter and other places and makes fantastic graphs that many people use, including climate scientists. And speaking of climate scientists, we're really excited to also have Leon Simons with us again today. And as you may know, Leon is a co-author with climate scientist James Hansen on a actually quite famous paper now, Global Warming in the Pipeline, and has done a lot of work on various aspects of climate change, including the fact that the reduction in aerosols or smoke from ships has greatly accelerated climate change. We've talked a lot about that, but we're going to be talking about different subjects today regarding climate science. And we're going to start off with what the title of this program alludes to, and that is something called CO2e, or CO2 equivalent. So many people know that burning fossil fuels has put more CO2 into the atmosphere. And CO2 is a greenhouse gas. It acts like a blanket around the Earth. And if you do the numbers, we put about 2.4 trillion tons of CO2. We've emitted about 2.4 trillion tons of CO2. But the oceans and the soils and plants absorb some of that. And the remaining is actually, I'm not even sure, like 1.1, 1.2, well, I think about 1.1 trillion tons of CO2 that remains after we emit it, after this uptake from oceans, plants, and soils. And if you take a look, there was about 2 trillion tons of CO2 in the atmosphere. Now there's about 3. And so we've increased CO2 by about 50%, almost exactly 50%, actually. Now that itself is a huge, big deal, but there's more than that, because CO2 is not the only greenhouse gas. And there's other greenhouse gases like methane and nitrous oxide, and they have different characteristics. They, per pound or per ton, they many of them warm a lot more than CO2, but they also don't last as long as CO2. And I always tell people that one of the most important things to know about climate change is that CO2 is not like other kinds of pollution that you're used to. If a factory is polluting a river and you used to go fishing and swimming, and you can't go fishing and swimming anymore because the river is too polluted, but then you get your friends and you shut down that factory, you get the politicians to shut it down. Next year, you go fishing and swimming again because the water will be clean. That's not CO2. CO2 lasts in the atmosphere for hundreds to thousands of years. So things don't get better when you stop emitting it, but if you're lucky, they just won't get worse. Now, that's a whole subject in its own right of how it's going to get worse, maybe anyway. But some of these other gases like methane, for example, much more powerful than CO2 in warming, but it only lasts in the atmosphere for about 20 years or so before things in the atmosphere break it up and actually turn it into CO2. So that's just a little bit of the background. And so because these different gases have different effects, we try to convert their effects into an equivalent amount of CO2 to get an understanding of, like, how many blankets have we added to the Earth in terms of warming? And that's what's called CO2e, E for equivalent. So with that background, Eliot has come up with some recent, calculations and things on that. So I'm going to turn it over to you, Eliot, to tell us more.
Well, thanks, Dan, and thanks for having me on. I've had a problem with this idea of global warming potential, GWP, for a long time, for years. And your invitation finally got me to do the calculations. So I am thankful for that. Let me just explain what global warming potential is, because that's where it all starts, right? So the idea is that industries aren't just going to emit CO2. They're going to spew methane and nitrous oxide and chlorofluorocarbons and all these other things. So the idea is, if you have a protocol, Kyoto Protocol, or something about how much GHGs you could emit before you have to, buy credits or whatever, then you need to convert everything to CO2. And so the global warming potential was created to be a pound for pound equivalence. You emit 1 ton of CO2, I'm sorry, 1 ton of methane, right? You emit 1 ton of methane. Well, that's the same as 24 tons of CO2 if you're talking about a 100-year period, or 84 tons if you're talking about a 20-year period, right? So it's really an industrial thing. It's not a measurement that was ever meant to really be used for CO2 equivalent. It's a pound for pound. And so I looked and looked, where can I find somebody doing a calculation where they convert GWP into CO2e, just as an example. And I will show you one of these, all right, that I found. Let me see if I can share this on my screen. How do I
be able to share? You're a co-host, so you should be able to share. Just go to share.
All right.
Pick the right screen.
Okay, here it is. So let me share this. So hopefully you can see that I am sharing a table from a paper, right? And if we look at this, then across the top, we see CO2 was 414, right? The methane and the nitrous oxide at the point this calculation was done. And then we look at the very bottom line, and you notice what this person has done. Let me just explain this. Is they took that 1,865 parts per billion of CH4 and converted it to parts per million and got 1.865 parts per million, as they should. And then they simply multiplied that by the number 25, which is the global warming potential, to get, well, it's at least 46.6 in CO2 equivalent, right? So they just converted a parts per billion to parts per million, and then voila, multiply that by 25. Likewise, they converted nitrous oxide parts per billion to parts per million, 0.332, multiply that by 298. That was the global warming potential. Add these three things together, the CO2 at the time, the CH4, this value, and the N2O, and you see at the very bottom of the screen, they say that means the equivalent's at least 560 parts per million. All right? Well, this is wrong. This whole calculation is nonsense. Right? And you have to start by understanding this calculation is nonsense. It's embarrassing. A climate scientist,
who did this, by the way?
A climate scientist who I don't want to name.
Oh, okay.
So we'll let
who shall not be named. Okay.
Shall not be named. I maybe you can see it in the tab up at the top, and don't look there.
Okay.
Okay. The point is that this is not a pound for pound computation, right? So a part per million of CH4 does not weigh the same as a part per million of CO2. And this global warming is all about converting a mass of something into a mass of something else.
Well, let's explain that, because this, I see this as being sort of a little education class for people interested in diving into climate change science. So when we say right now, CO2 is about 425 parts per million.
Right.
And that is number of molecules, right?
Right.
Versus other molecules that are out there.
Right. The different molecules weigh different amounts.
Right. So different, it would be like, what would that be like? You have a number of cars, what percent are this kind of car versus another? And some might be trucks, and some might be little motorcycle, whatever, vehicles. And then each vehicle weighs a different amount. So you can't just say, well, 20% with this, and that's how much it weighs. No, you have to know how much the molecule weighs.
So
let's also to keep going on this, just to clarify terms and everything. But when we say CO2 is 425 parts per million, that's another way of saying that 0.0425% of the molecules or CO2. It seems like a small number. It's actually trillions of tons, so that's one way of putting it. And also you have on here parts per billion, and we can convert that. So you have methane is 11865 parts per billion, which is 1.8 parts per million.
Exactly. So they had to do the parts per billion to parts per million change, and then he just multiplied it by this number. So let me get back to the weight of things, all right? So
before you do, I just want to make sure that we're talking about parts per million volume, ppmv, right?
well, yeah, we're excluding water vapor. I mean, that's excluded from the computation. But yeah, you're talking about not per volume, but per million particles, how many of them are this other molecule.
Yeah, so okay, so when you're dealing with ppmv, that's a volume ratio, and the volume that's occupied by a gas molecule when you divide, right? That's the same regardless of the mass of the molecule.
But that's not what we're doing here, right? That's not this number. This is, any rate. Let me just give you these fractions. So CO2, right? CO2 weighs, it has what's called an atomic weight of about 44. Whereas CH4 has an atomic weight of about 16 or something. I think you can look that up. So you have to convert the weight of one to the weight of another. And if you look this up, there's something called the mole fraction ratio. And essentially what you do is you take the weight of one and you divide it by the weight of another, and that gives you an extra factor you have to put in there when you're applying the global warming, this GWP, global warming potential. So, I did all this math, and all I was really trying to do, so you understand, is to duplicate this table right here. This is a NOAA table that is saying that the current CO2 equivalent as of 2022 is 523 parts per million. All I wanted to do was duplicate, was to find that number. How did they get 523, right? And you see it there. It's like, and you look and it says, well, that's CO2 plus non-CO2 greenhouse gases in parts per million. And so that was the computation. I don't want to lose people. I don't want to lose people in your audience. We'll go from having 100 people watching this down to 3 if I go too deep into this math. But what I want to say is that I spent considerable time and energy doing this computation. And I did it in 2 different ways. One way I did this computation was to say, well, let's look at the instantaneous CO2e back in 1750, using all of the greenhouse gases that were in the atmosphere at that time, however much methane and everything. And let's find the total CO2e as of 1750. Let's compute the total CO2e as of today. And that will tell us, the rise in greenhouse gases. We take the total CO2e and the total CO2e. But there's another way to do it, and that's what this chart has in it. And what this chart does essentially is it says, no, what we are really doing is we are using the 17 values of 50 values for these other greenhouse gases as an absolute baseline, that they are essentially zeroed out in 1750. And we're simply looking at how much all the other greenhouse gases have gone up since 1750. So you have these 2 different competing ways of doing it. And I did it both ways, right? And there's one other thing, and we spoke just before we went on the air about this. And before I sort of show those computations, I want to unshare so we can have this conversation maybe just for a second so everybody can hear it. And that is about how frustrating the whole concept of global warming potential is.
Wait. Let's also start again, because not everyone knows what GWP, global warming potential, is. The multiplying factor that you give to a greenhouse gas that's not CO2 to make it equivalent. And actually, CO2 has it too. It's called one. So, one molecule of CO2 equals one molecule of CO2. But when you have methane, methane is very much more powerful. We're going to talk about that. Somewhere over 100 times as much warming per molecule as CO2 has. However, unlike CO2, which lasts essentially forever in the atmosphere, hundreds of thousands of years, methane lasts like 12 to 20 years. And so what they try to do is they lower the instantaneous warming that you get when the methane molecule is in the atmosphere and try to account for the fact that it goes away over time. And so over 100 years, even though the warming is super powerful in the first 15 years, it's very little in the last 15 years. And that's what this GWP, which should always have a number after it, the number of years you're looking at.
Yeah, it defaults to 100.
GWP 100 means what is the average warming of methane over 100 years? And GWP 20, and that number is around 30. GWP of 20 years is about 86. And GWP 1,
which is what I computed. That's what I just computed.
I just wanted to define our terms so we don't just use terms without defining them for people.
So the stupid thing about GWP, right? It's really stupid, is that we are constantly replacing methane as it decays with new methane. It's not just like the methane molecule says, oh, I'm old now, I can't react anymore, right? So yeah, this whole idea of GWP kind of assumes that we come to a complete zero stop now and just let everything decay from here. But if you keep replacing and replacing and replacing, you're essentially always at GWP 1, right? Well, GWP 0, because of how the equation works, is like a Dirac function. It actually is asymptotic. So GWP 1 is 140, all right, was what this computation showed. So, it's one of these things where really, if you want to do any conversion at all, you should use this fact that we are constantly replacing old methane with new methane, that methane has a current value, and it's the current methane in the atmosphere that is warming the atmosphere, not some decayed methane 20 years from now.
So why use global warming potential in the first place and not just concentration?
Because I'm trying to duplicate what NOAA did just for my own education so I can understand what CO2e is, right? I mean, CO2e comes from GWP. It's part of the calculation, at least the way NOAA did it. So let me just give you the bottom line, and then we can not have to see numbers anymore, okay? How about that? And
okay.
or at least these particular numbers anymore.
Still numbers for it.
So what we see at the top here is my computation of CO2e as of the April 2024 values. And below it is the computation of CO2e pre-industrial, where I add in all of the levels of the greenhouse gases that existed at the time, right? So if you look at the CO2e for everything in the atmosphere today, I mean, I'm not doing other things that, all the minor gases that also add up cumulatively. There's certainly, and new water vapor and all those things. But if you add everything together, you get 623.8 versus 389.2 for a gain of 60.3% in CO2e. If you do it the other way, and this is what Leon suggested, all right, and is really, I think, the way that NOAA did it. What you get, and here this in the bottom, I am absolutely zeroing out. I'm assuming pre-industrial is a zero benchmark and going up from there. And when I do that computation, I get 507.7. So in other words, CO2 has risen equivalent from about 270 to about 507. And, NOAA had 523, but if you read their little chart, they include all the trace greenhouse gases that I didn't include. So I think the difference between what I got and what NOAA has is all the other gases that they included. So I'm satisfied with this computation, as grotesque as it is, but you see that it's using GWP of 1. in it, right?
Everything is GWP1.
Everything is GWP1 in this computation. So, this is the math, and if, give me a chalkboard and not wanting to bore the audience to death, and I would go through each one of these columns in detail and explain it. But, it just shows the fact that this is not well known, it's not publicized, it's not available. There aren't examples. The one example that is out there is just wrong. It is a very frustrating thing for me. And I would love it if there was more just sort of discussion about these numbers at a level that was both correct and definitive, rather than having these super important numbers just hanging out there, kind of loosey-goosey.
I think
I have some comments, but let's
I think it's
Leon
covered
go
quite
first.
well. I think it's covered quite well in the IPCC reports, and also in our global warming in the pipeline paper. You can read about it. It's I think the best way is to look at the radiative forcings of the different gases that are in the atmosphere, then convert it to CO2 if the CO2 would have the same force. And I guess explain it maybe in a minute, maybe, but I'll first let Dan finish what he was saying.
No. I was going to say I have some comments, but I wanted you to first comment, Leon. So
And I need to comment also. Okay.
Okay.
So the
We'll
only place that the mass ratio really comes into it, because everything else is gas molecules in the atmosphere. So that's ppmv. Okay. When you want to go back to tons of methane or tons of CO2, then you have to adjust for the relative molecular masses. So if you're doing it in that table, you've done it.
Actually, I think you're wrong. Here's the definition from NASA. It's important to understand that parts per million, quote, refers to the number of carbon dioxide molecules per million molecules of dry air. These measurements are from the mid-troposphere, the layer of Earth's atmosphere that is 8 to 12 kilometers, about 5 to 7 miles above the ground. So this is not V, that you could have ppmv.
No. So that's exactly saying what I'm saying. Those are molar ratios.
Right. The number of molecules,
so
that's what we were talking
everything
about.
In molar.
Yeah.
That's right. So you can keep everything in molar ratios until you want to go back and calculate tons of something.
Okay. I'm not sure what your point is, but okay.
Well, the point is, if the last column was multiplied by the mass ratios, then that's doing it in the wrong place.
So
I'm not.
I didn't multiply any column by mass ratios, but no, I all right. I don't know exactly what you're saying.
Yeah, we're not following that. By the way, I'm going to say something about your calculation, so this is, maybe people didn't catch this, but the amount of methane in the atmosphere right now is about 1,800 parts per billion, or 1.8 parts per million. And by the way, let's compare that to the amount of CO2 in the atmosphere, which is 425 parts per million. So the amount of methane is 1.8 versus 425. You'd think, oh, the warming from methane must be very tiny, because, it's such a tiny amount compared to the amount of CO2. But methane is a super powerful greenhouse gas. So even though it's only 1.8 parts per million, it's about 2/3 the warming of CO2. And that gets back to this 140 number that Eliot mentioned earlier. But however, what we're trying to do is calculate the equivalent amount of CO2 versus the amount of CO2 that used to be in the atmosphere pre-industrial, which is around 280. So when we reach 560 ppm of CO2, we will have doubled CO2 itself, not CO2 equivalent, but CO2. We're at 425 now. So we've gone up around 50%. But if I want to calculate CO2 E, and I want to know 280 versus what it is now, I do want to zero out all the other greenhouse gases pre-industrial and only look at how much they have increased. So methane pre-industrial was around 700 or 0.7 ppm or 700 parts per billion.
If you look at the bottom,
you did that.
You look at the bottom chart and you'll see I have a gain. So I have the pre-industrial parts per million, which is 270, 700 parts per billion, 270 parts per billion. Then I have the gain since the pre-industrial in the next column over. So it's the gain, and then I multiply that by the molar fraction to get the total weight, multiply that by the global warming potential to get the net contribution. All right, so that's kind of how the computation went here.
So you did but did you zero
so the bottom
well,
chart
wait a second, but did you zero out, but you zeroed out CO2 also
at 270. So CO2 started at 270, it gained 153.
Okay, but then to get where we are now, you have to add 280 to that number. If you zeroed out CO2. So you don't zero out to do CO2e, you don't zero out the CO2 because again, if it was CO2 only, we would say it was 580. It's 560 versus 280.
So what you're missing, yes. So on that final column, the net, if you add up all those numbers, 153, 62, 20, and 1, I then also added back in the 270. All right. So that
280. Where's that?
Well, 270 is the value that NOAA uses for 1750.
Oh, okay.
So
close enough.
Yeah. So that right-hand column is not a pure sum. It's a sum of those four numbers plus the original 270.
So the 153 column, let's take that column. The net of CO2 at the very bottom there on the right side, it says 153.7.
Yes.
That is total CO2, not with the 270 deducted. Is that yes or no on that one?
That is no. That is just
then tell me again where the 270 is added in, or is it not on the chart there?
I'm sorry for this confusion. It's hard to lay this out in a way that really explains.
Oh, I see. If I add up those numbers, they don't come up to 507.
No, that's right.
So you added in 270 at the very end, but didn't show it.
Yes, thank you.
Okay.
I'm sorry for my bad academic presentation here. My fault. So you add back the 270. I want to say a quick word about Leon's method, because I certainly, agree that is like totally probably the better way of doing this, which is you figure out the forcing, which is essentially this AGGI number, right? The annual, the greenhouse gas index, how much has forcing gone up compared to the 1990 sort of baseline. Let's figure out, based on that, how much equivalent CO2 would generate that. The one problem I have, and maybe Leon could explain this, is that it seems to me that methodology that Leon, and let me just unshare this because that's, we don't need to see this anymore, that the method that Leon is using needs to know the ECS and work backwards from that. Is that true, Leon? It seems like you would need to know the ECS in advance.
No. No, that's different. I can explain it here.
Okay, go ahead.
Yeah. So first you have the forcing, and then the question is how much warming does that forcing cause? And that's a different question. So someone was asking in the comments, like, why is this important? Why are these numbers important? And I would like to explain that. So what we are really discussing here is what causes the climate to change. And as in climate science, we say what forces the climate to change. So what are the forcing agents, radiative forcing agents that push the climate in a certain direction? And greenhouse gases, if you increase the amount of greenhouse gas in the atmosphere, you push the climate into a warmer direction. And we call these radiative forcings. So I will share my screen, and I'll show you what a few figures, both from the IPCC and some I made from the IPCC data, which I hope will explain this. So I think, in my opinion, the right approach to this question in more detail. And
let me comment. I just want to comment. Go ahead.
I will also show why we, or I think, including the IPCC, think the forcing has gone up by so much that would be equal to if CO2 had doubled from what it was in 1750.
Yeah, and what we're doing here, by the way, is we're calculating, like if we assume there was one blanket of greenhouse gases around the Earth, pre-industrial, and that was good, by the way. Without any blanket, we would be a frozen snowball. There wouldn't be any life here on Earth, except for maybe ice life of some kind. So the fact that we had a blanket made a very good climate for civilization to develop, and that was great. Starting around pre-industrial time, we started adding greenhouse gases, and we're calculating essentially how many extra blankets have we added to the Earth to warm it up. That's what this CO2e calculation is, just to put it in context for maybe some people that don't want to get into the nitty-gritty of the numbers. But go ahead, Leon, go share your screen.
Yeah, but it's not just about numbers, it's about what these numbers represent.
Yeah.
And that's crucial. You know, the numbers. I'm not going into all the algebra and all the difficult physics. You can read our global warming in the pipeline paper if you want to go there, and most won't. If you won't, I still recommend you to read the global warming in the pipeline paper, but maybe skip a few pages. But let me get to it.
Okay, go ahead. You were sharing. Go ahead.
Yeah, I'm sharing again, right? Yeah. So these are effective radiative forcings from 1750 to 2023. So in 1750, that's about when gradually the Industrial Revolution started. So that's the baseline. So the number, if you look at 1750, I will show you in the next slide, but stick here with me for a bit. There, the number is 0. The climate, because that's a baseline. So the climate was not pushed in a certain direction relative to that, because that's the baseline we use. So there it was 0. And there the CO2 concentration was 280 parts per million. And I'm mainly using round numbers here just to keep it easy, or relatively easy. So here we have carbon dioxide, CO2. Most of you know that, and that's about 2.3 watts per square meters. So that's the majority of the warming. Global warming is caused by CO2.
And those are error bars there. You might want to point that out. Point out the error bars, because you assume not everyone really knows the science very well.
Let's first do this. Let's first just show you the bars. So these are the bars. This is effective radiative forcing. So these numbers are important. These show how much extra energy is forced into the climate system on average over each watt of the Earth's surface, which is 510 trillion square meters.
Meter, how many square meters of the Earth's surface? Yeah.
Yeah, square meters. So there's CO2, there's 2.3. Then you have all these other greenhouse gases, methane, N2O, halogens. So these are other gases. But there's also ozone. And most of you know ozone from the ozone hole and from the stratosphere. But this is actually ozone in the troposphere, where it acts as a greenhouse gas. And then there's stratospheric water vapor, which it also causes a bit. But so these are the main greenhouse gases. And NOAA just looks at these for their index, because they want to have an index and to show, okay, how does it change over time? But if you really want to know what is the total effect of all these greenhouse gases, you have to add these numbers up. And you get to 4 watts per square meter. And that's the same number as what the CO2 forcing would be. It would be 4 watts, about here, if the CO2 concentration doubled from 280 parts per million to 560 parts per million. Of course, that's not what happened yet, but the greenhouse gas caused that. Now this 4 watts per meter number. But this is the total anthropogenic effect, total human caused effect. This is not yet at 4 watts per square meter. Again, sorry, this is the update from the IPCC analysis looking at the radiative forcing from Forrester et al. And Chris Smith.
I have a question for you about water vapor. So warming increases water vapor in the atmosphere. It's up about 10%, I guess, because we've warmed about 1.5 degrees. And you have stratospheric water vapor, but why isn't I know water vapor varies hour to hour, minute to minute, day to day, but on average it's 10% more. So why
stratospheric water vapor is a forcing? So that's a result mainly of more methane in the troposphere, which also increases the amount of water vapor in the stratosphere. So that's a forcing. That's calculated here as a forcing. But water vapor in the troposphere, which is from ground level to about 10 kilometers above the surface, where the rain, the weather happens. That's a feedback, because because the Earth warms, there's more evaporation, but also the atmosphere is warmer, and a warmer atmosphere can hold more water. And water vapor is a greenhouse gas, and with that, it's called the water vapor feedback, which is
correct. Where's that factored in?
Which is the strongest positive feedback. So, and positive here means causing more warming. The strongest negative feedback is that as the planet warms, there's more radiation, because if a surface heats up, it will radiate more heat. And if the planet heats up, it will radiate more heat very fast. And so that's the strongest negative feedback, which reduces the warming, let's say.
So this is forcing, not EEI, I guess is what you're saying. The EEI would take all that feedback into account.
The Earth Energy Imbalance is different. I will show that in one of the next slides.
I'm just wondering where it's included, but go ahead. Keep going. It's great.
Leon, I have a quick question about this. You mentioned that 4 watts of forcing is equivalent to doubling the CO2. And that's where, I guess the thinking is that watts per meter squared generates a certain amount of heating on the planet. CO2 generates a certain amount of heating on the planet. We compare, some known value of CO2 heating to, rate of heating to 4 watts and see how much CO2 that means. And that's where, to me, I thought the ECS came in, and you're saying, no, it doesn't.
No, the Earth climate sensitivity is how much warming does that forcing cause. And that doesn't relate to how much forcing does a greenhouse gas cause. There are steps here. So first you have the change in greenhouse gas concentrations. Then it's like how much forcing does that cause? How much energy does that change into the system? And then how the system responds. So then there's feedbacks, as I mentioned, the water vapor feedback, the temperature feedback, ice feedback, cloud feedbacks. And that all results into a temperature effect. But first you have the forcing, and then you have the feedbacks, and then you have the temperature change. And the temperature change is how sensitive the system is to a certain forcing. It's not the forcing comes first. But I think I will explain it more in the next slides.
Okay, keep going. But is it safe to say there's forcing, and then forcing leads to an energy imbalance, which includes the feedbacks, and that energy imbalance leads to warming? Or let's keep going. I guess.
Yeah. In short, So these are time evolution. So here I just showed what the number of in 2023 was relative to 1750. So in 1750 it was 0. In 2023 it's these numbers, for which the greenhouse gas add up to 4. And I was starting to say, okay, this doesn't show 4. Why? Because there's other things involved, which include land use change, which causes increase in albedo, which means more sunlight is reflected back to space by the surface. And then, so this doesn't include sea ice or snow change, because that's a feedback, but it is a forcing. And then, and forest change, for example, if you have more growth, that's also a feedback. But then there's aerosols, which is very uncertain. So this is the uncertainty range. So this is the biggest uncertainty in climate science. That's one of the reasons why I think it's so important to do research on this, and to get this to decrease this uncertainty. And that relates to the climate sensitivity, because if there would be more cooling, then the warming we see now will be caused by less positive forcing, which is here. This is the total effect of all these, the sum of all these parts. And again, there's a big uncertainty bar, and that uncertainty is mainly driven by the aerosols, which reduce to 1. So we don't know if it's the forcing, the radiative forcing, which causes current, energy imbalance, and temperature.
So Leon,
we know if that's 3 or 2.
Please forgive me for being super naive and uninformed about this. But I mean, is there an actual equation that shows, the delta between 270 and current carbon dioxide equals so many watts per meter squared? I mean, I'm thinking that there should be the way you're using it, to work back to CO2 equivalent, is you're saying, well, there is an equation I can write down that says if you plug in this many watts per meter squared, it will output this much CO2e. I gave a spreadsheet to, naively try and create that equation for NOAA data.
It's 4 watts per square meter. So I'm just using round numbers here because everyone.
But I'm just asking.
I shared the paper with you already, but for the people listening, it's 4 watts per square meter. That's also what the IPCC says, and that's, I think we use 4.1 or so the round number is 4 watts per square meter equals 560 parts per million, which is double the CO2 concentration from 280 parts per million.
So can you cite this source on that calculation? I'm just really, I'm not doubting it in the least. I would love to see that. I know doubling the CO2. So doubling the CO2 will lead to a certain warming, and I'm aware of that, dating back 150 years, that double the CO2, you get so much warming, but I'm not really aware of double the CO2, you get so much watts per meter squared, in forcing. And that's the, equation that I'm wondering about.
Yeah, it's that's like the basics. You cannot get warming without the forcing. So that's really the basics of the change that's happening. But again, you can look at our paper. I think that I've shared it already with you. It's in the first pages of global warming in the pipeline. But I think you can also read maybe the 1980 paper by James Hansen about this, or 1990, where he also covers sulfur, right? So the forcings are always covered, but this is always part of the discussion of what causes the climate to change. We first need more energy in the system before the temperature will go up. It's that simple, right? So you need to increase how much energy goes into the system before your thermometer will show an increase over the next decades.
By the way, I have a question. So this shows, go back to the last one there for a second. So the CO2 line at the top, it's about 2.2, and we're about halfway to a doubling. So if we doubled it, we would be 4.4. You're saying it's 4. I'm assuming that the second half has a little bit of a logarithmic impact, so the second half doesn't have as much impact as the first half of the additional CO2. Is that correct? 'Cause
Yes.
CO2
Yeah,
is a
it's
logarithmic.
logarithmic.
Yeah, right. So that's
Logarithmic.
why it's 4, not 4.4. When you said
For every doubling causes a forcing increase of about 4 watts. So that means that it's logarithmic.
Every doubling, okay.
Every doubling. So if you want to again to double the CO2, so the forcing from CO2, you would have to emit 2 times, or you had to add 2 times as much CO2 to the atmosphere as you did from going from 280 to 560.
Yeah.
So that's important.
The way I think about it, if you had sunglasses that cut 50% of the light, and then you put 2 of them in a row, you're not going to get all the light gone. It's going to be 75% of the light from total, and that's the same thing with CO2 logarithmic.
Yeah, so it is. So it's for me. I was thinking, how do you explain this logarithmic effect? So this, because I think many people find it difficult to understand.
Yeah, tricky.
If it is like really simple. If you have a light bulb, if you go twice as close to the light, if you reduce your distance between you and the light bulb by half, the light is shining 4 times as bright. If you moved close to the sun, if you reduce the distance between you and the sun by half, the sun is shining 4 times as bright. Also, the gravity from the sun on you is 4 times as much. This is really basic physics.
Right.
And the same happens with it's not the same, of course, but similar thing happens with greenhouse gas concentration. It's not linear; it's logarithmic. So it's not this. It's not a regular line, but because the CO2 emissions have been increasing, the forcing line is quite linear from CO2 over the past decades. But then of course we have the aerosols, which have decreased, which made this line, the forcing, not increase linearly, but more than linear and increasing. So a faster rate of increase than there would be if you would just have the greenhouse gas concentrations increase.
So Leon, I just want to thank you and stand corrected, because I did a quick Wikipedia search while you were explaining this. And if I could just read this quick paragraph. It actually is even worse than what you said, according to Wikipedia. It says the radiative forcing caused by a doubling of atmospheric CO2 levels from pre-industrial 280 parts per million is approximately 3.7 watts per square meter. In the right, and it says this figure is straightforward to calculate by using the Stefan-Boltzmann law and is undisputed. So
yeah, so no, but there's uncertainty there. So I think IPCC uses 4.1, and so
yeah.
That's why I use the round number. I say
4 is fine. Yeah, okay.
I was having a discussion with someone about the first scientific papers, and there were no decimals, right? There were about climate change. There were no decimals. So why use decimals? Right? Because it was just a few pages, and now we have these 16,000 page reports with a lot of decimals, but the basics we knew already. We've known that for indeed over 150 years.
Yeah, again, Svante Arrhenius published the first paper on this subject in 1896, and he did all calculations by hand. He said the question was, how much would the world warm if we doubled CO2? That was what his paper. And by the way, it wasn't called carbon dioxide back then. It was carbonic acid, which is the same thing. It's just a different name for it. And he did that calculation. My understanding, he got it about right. I mean, roughly. I mean, within some reasonable margin of error. And that was 1896. No computers, just by hand, using the kind of numbers you're talking about.
No distractions, also.
No Twitter.
So let me get back to this. So I think it's good to just cover the basics. So 4 things, right? If you look at these from 1750 to 1850, not much happened. It was mainly the United Kingdom starting to industrialize and emitting greenhouse gas. But some things happened, of course, and that's these lines. So the big black line is anthropogenic, the human-caused forcing. But these black lines, so the thin black line, is a total, which here is mainly caused by volcanic eruptions, putting a lot of sulfur mainly and other dust particles into the stratosphere, where there's no weather happening, and where these particles stay for many months to years, and pushing the climate temporarily into a colder state. And if there's no if there are no volcanoes going off, then there's a warming effect, because there's no cooling, right? So that then this is positive. If there's a long time without volcanic activity, you will have the green line is above zero. Of course, there's some greenhouse gas being emitted, but that's compared to the industrial emissions, it's negligible. And then all these other gases, I won't go into details here, but I think the most important line is the net effect and the aerosols effect. So here there's carbon dioxide in purple, but the net effect is a total from all these different forcing agents, and the aerosols are reducing the total effect. And I think what's helpful is to look at CO2 equivalent. If you add up all these greenhouse gases, which I did in the first slide, showing all these different, which add up to 4 watts per square meter, let's say today, then, and including the ozone and the water vapor, and of course that's mainly ozone, then we would already, if you just look at greenhouse gases, we are already at a doubling of CO2, because we are at 4 watts per square meter. And if you use that 3.7 number, we are even higher. 3 point, whatever.
Leon, quick question for you. If I could just ask you your opinion on something, because we both essentially should have arrived at the same number, right? If these global warming potentials are correct, and you have to assume they are, then both calculation methods should get you the same thing.
I haven't looked at your math, but I think this global warming potential is different. It's really looking at the different the emissions of, and then
it had an industrial purpose for
but
it's
confusing.
It's actually the way that CO2e is defined. I think your calculation is certainly more in the spirit of what CO2e should be.
No, but
the actual calculation, that NOAA does is from the other.
GWP has time thrown in, and what Leon's presenting is what's happening now. This is this year. It's this much
concentration. I think that's also what NOAA does. But I would have to look it up, and I can do it later. But can I just cover these slides, and then we can go back to
keep going. Great, that's great. And hit on that pink line as well.
The answer of Dan's question also hidden here in the purple. So, but I first want to cover the forcing agents. So here's starting 1850 to here's 2022. So as we mentioned in Global Warming in the Pipeline in the paper, the greenhouse gas concentration is already at equivalent of what it would the effect of a doubling of CO2 would be. That's what the red line shows in the 4 watts per square meter. But the net effect is not yet there. Why not? Because that's then you deduct this line, the orange-yellow line, from the greenhouse gas effect. And I'm not taking all the very small parts, the surface changes. I'm not including them here, just to keep it a bit simple. Then you have 4 minus 1 is 3. Easy math, right? And then that's what you get here. So around 1970, the aerosol forcing stopped increasing, so stopped becoming more negative overall. So that's when global warming started really to become quite visible because there was less cooling from air pollution, so less sunlight being reflected to space by air pollution and by clouds, which got more bright and bigger because of this air pollution. So that stabilized, and then so that's also when the net effect started to increase much faster than between even 1750 and 1970. But now around 2010, the aerosol cooling, the negative forcing started to decrease because especially China started to rapidly reduce the amount of air pollution, especially by installing desulfurization system with its coal plants and cleaner cars and filters, and so that's when this line keeps increasing more. And I think this is even an underestimate, and that could be because this was more negative. So if the cooling was more, that could also, then this would have been lower. And then if you reduce aerosols more, then this line goes up more. And then because also we've discussed it before that shipping regulations in 2010 and 2015 reduced aerosols over the oceans. And the United States moved from coal to gas because of all the fracking. China again reduces air pollution, and other countries too. Only India has kept increasing its air pollution, but also has plans to rapidly reduce its air pollution. So this causes this line to go up, and so this is the net. This is the observed. Sometimes I still have some difficulty with some words in English. Not my native tongue, sorry. So this observed increase in the energy imbalance of our planets with NASA satellites, which are coupled to ocean heat content and surface energy balance data. And this shows that there's an increase, which means that there should be a faster forcing increase because there's such a jump that a lot of energy is accumulating much faster and faster in the Earth system. And what's interesting to look at here is what causes this increase, because this is just, of course, one data point. But if you look at here, it is the annual data. Here I showed the 48-month average, and here's the annual data from absorbed solar radiation, now starting in 1950, because the satellite data is only available since 2000. And then you see that here there's a big increase in how much sunlight is absorbed by our planet, especially over the last years, most recent years. Since 2010, and then especially more recently, there's really a huge jump. But there's a decrease, so it's a decrease in outgoing radiation, but the line is negative. That means that more heat is radiated to space. But I made it negative to show that heat is leaving the system. Because of course, then you can compare it to these. But maybe it's always difficult to explain these numbers, and there's different ways of presenting it. So there's more heat leaving the system in the infrared band, but there's also much more sunlight being absorbed. And if you deduct this, or you add up -1 plus 2.3, you get 1.3. So over the last year, the energy imbalance, so how much heat was added to the Earth system, this relative to 2000 to 2009, was 1.3 watts per square meter higher than between 2000 and 2009, the first decade of this century. That's a lot of additional energy accumulating in the Earth system. And this is from Forster, a recent study, an update of this NASA, of this IPCC analysis. And here they show that the lowest number in, I think, 8 years. I think this is completely wrong. think it's completely wrong because they use a simple climate model.
The aerosol number you're talking about, the
the aerosol
yellow
number
line.
is most negative it has been in 8 years. Well, we had all these reduction in air pollution over the oceans and in other places, and I think this is very wrong. And one of the reasons it's so wrong is because they included the wildfire smoke from Canada, and they put it into the simple model, which pretends that it's a global averaged blanket, let's say, that's reflecting sunlight instead of that's not the reality, of course. The reality is that these forest fires were mainly over Canada and also and that's very different from, for example, reducing air pollutions by shipping, which are all over the oceans. And
the ocean is dark, and if you make it
lighter,
lighter,
it's a big absorbs 90% of the additional energy in the system. So I think that's why this number, I think it's wrong, and especially, of course, because of the data.
Can you talk a little bit about? I just want our audience to understand the meaning behind these numbers. So the yellow line is how much energy, how much sunlight the Earth is absorbing, and I think from
relative to this, relative to the first decade of the century. So how much?
I see. Okay, but it's going up, and it's going up because I think you're saying that
because the Earth is getting darker. So that's really simple, because there's incoming sunlight, and if there's less sunlight being reflected back to space, that means that more sunlight is being absorbed by the Earth system, and there's a few tenths of a watt of an increase in solar activity over an 11-year period. So now the sun is a bit more active. So but it was also 10 or 11 years ago, and you didn't see that spike then. So
something else did this. Yeah.
Sorry?
Something else happened, right?
Something else happened, which is mainly a reduction in cloud cover, a reduction in air pollution, and then the next question is, what causes this reduction in cloud cover? And of course, there's also a reduction in sea ice. And cloud changes are also feedback, but also because there's these interactions with aerosols, it's also forcing. That makes it very, very difficult. And I can talk about, I think I did it already before here. I can talk about hours about what causes all these uncertainties, so how much natural aerosols are there, whether it's Sahara dust, or whether it's algae emitting sulfur, or whether it's pollen from trees, or these forest fires, and then you can discuss whether these forest fires are natural or not. So there's a lot to unpack there if you like, and we've done it before. But so these are the four. I think that I'm just. Can we
talk about a moment about the red line?
Compare it to the greenhouse gas forcing. Because you have this greenhouse gas forcing, which causes the Earth to warm, and then this has been going up quite linearly, almost linearly since 1970, as I mentioned before. And this line is not as linear, but it's close to linear. But then what is causing this? And I think we think, so as we publish in our paper, we think that the aerosol forcing is underestimated. So that's probably that there was much more cooling, about 2 watts per square meter of cooling globally around 1990 to 2000. So around this time, there was more cooling, which causes more warming if you reduce this forcing, or make a net forcing increase if you reduce the negative forcing from aerosols, a stronger negative forcing from aerosols.
Let's talk about the red line for a second, because first of all, it says decrease, and it's a decrease and it's negative. So you really mean an increase in infrared radiation to space. And the main thing causing that is as the Earth warms, the amount of heat it radiates to space goes up with the 4th power of the temperature. T to the 4th power, which is a very strong
in Kelvin, temperature in Kelvin.
Yeah, in Kelvin, but it's a very strong, powerful way that the Earth stays in energy balance, because the warmer it gets, the more it radiates out, in a
Yeah,
very
and that's an
powerful way,
important reason
but
why
we're still
why the
overwhelming
climate.
that. Yeah,
That's an important reason, of course, why the climate has been quite stable over
right,
millions,
exactly.
hundreds of millions of years, because there's a lot of outgoing radiation when you increase the temperature.
But we've done a good job of increasing the blanket, keeping that warming.
Yeah, so you would think that this number would be positive, causing more heat to accumulate in the system because more the greenhouse gas concentrations are increasing, keeping the heat in, but it's negative. So it's decreasing. So more heat is leaving the system in the infrared because of the increase in temperature. But this is not what most climate models don't show that. And if you take into account a strong aerosol effect, then the models are closer to what we see here. Because for example, I have many climate scientists following me, and many on Twitter, for example, and then I've been talked about this quite a bit over the past years. And then when I had a poll a few months ago asking, do you think that outgoing long-wave radiation, the heat radiation to space in the infrared, has increased or decreased? 75% thought it would have decreased. So that less radiation would go to space. But we see more radiation go to space, reducing the heat in the system. And that's because, but this is a very important but. If you look at the increase in absorbed solar radiation, and you have this number relative to this number, so if you then there's an increase relative to how much sunlight is absorbed. There's an increase in how much of that sunlight that's absorbed stays in the system. So from that perspective, the greenhouse gas effect is increasing. But that's not. Then you really have to understand what these numbers mean, right? So, and I think it's maybe I'm not doing it right, but I've seen it more often that it's quite difficult to explain to most people what these numbers mean. So why? Of course, we're still learning. We're still, for example, something that I said that the effect of shipping would be very strong. I said it could be strong. I didn't know, but now because of this big increase in how much sunlight is absorbed over the past years, I'm afraid. So as a human, I'm afraid that that this effect is much stronger than most thought it would be, because especially because it's also this increase in sunlight absorbed mainly happens over the regions where most of the shipping was happening.
Right. Yes, and this is back. We've talked many times about that.
Feedbacks and all the other things. So, not saying it's all because of this, just as a disclaimer, but this is This is really a worrying. I think much more worrying than any surface air temperature or sea ice or whatever number you've seen in the past years from all these records being broken. I think this to me, this is the most worrying number, and it has been.
Now, it's also the one that we can address with solar radiation management or sunlight reflection methods or solar geoengineering, where we can artificially put sulfur particles in the stratosphere. That most of this aerosols are in the troposphere, in the lower atmosphere, where they fall out of the atmosphere in a week. But if you put them up in the stratosphere, they last for about a year, and can do a lot more cooling than per ton than if they're in the lower atmosphere. And that would lower the yellow line and get us back.
That would cause more sunlight to be reflected to space. That's true.
Right. And we could get that line down to zero if we wanted to. I mean, if we did put enough up there.
Yeah, but that's a different subject. Right. Let me just finish this. And this is the same. This is again forcing, and it is this over the past 130,000 years. Is again from our global warming in the pipeline paper, and I've added this the increase from so this all relative to 1970. So to
1750.
Yeah, 1750. Yeah, sorry, 1750. So then you see, of course, and I think this is a really important number. If you see during the Ice Age the last glacial maximum, as we call it in the sciences. During the last glacial maximum, the greenhouse gas forcing, so how much cooling how much the greenhouse gas, the decreasing greenhouse gas concentrations in the atmosphere, as they are measured from very small air bubbles from ice cores from Greenland and Antarctica. So if you look at these greenhouse concentrations and you assess how much cooling that would have caused, that's the lowest it has been, is about -3 watts per square meter. And now we've increased that to
Well, also civilization developed between the 10 and the 0. So
yeah,
basically, when civilization developed, the number went from like 0 to maybe minus 0.5 at the most, 0.4.
Yeah, and so if you look at past, like this one, if you look at the past glacial, interglacial, so this is called the Eemian, the last warm period, when sea levels were about 5 to 10 meters higher than they are today. Then you saw there was a decrease after this warm period, as there has been every time there was a warm period. After that, there was a cooling period. Mm-hmm. And that, so we should have expected this to happen again, but then it started to increase about 6,000 years ago. The greenhouse gas concentration, the greenhouse gas forcing started to increase.
Right, you're right. You're saying that in your paper or after the paper, it's not natural. It's probably humans growing rice, which gives off methane, cutting down forests for animal grazing, which turns, changes the land.
If you're interested in that research, I think, you can look at our paper, and we mainly reference Rudiman et al. There. So they've looked at it in lots of detail, and they compare it to all these other glacial periods and warm periods, and then they show that the greenhouse, the gas concentration should have been decreasing if you compare it to the other periods, but it has been increasing instead. And what was the biggest change compared to the past 10,000 years relative to all the other interglacial and glacial periods? That's humanity burning a lot of trees down, killing all the megafauna, changing the planet in many ways, especially over the past 6,000 years when you see this jump. But there's
can I just say again what you just said, but in a slightly different way, so everyone can get something out of this here that is kind of amazing, is that starting that peak at 10, it started going down a little bit, which would be consistent with past periods like the 130,000 years ago. And it would have slowly been going down again towards the next ice age. But instead, around 6,000 years ago, something happened, and we ended up with an extremely stable climate because it sort of the Earth by itself would have been going down. But humans were actually starting to change the climate, and it kept a sort of a stable climate until pre-industrial, when we went crazy and started emitting greenhouse gases like there was no tomorrow, and that might end up with no tomorrow.
And people might wonder why this is going up and the climate was stable. And that's something which is called the Holocene temperature conundrum. This is the Holocene, this period is called the Holocene. So the relatively stable global temperatures over thousands of years. Well, this was increasing. And so that's a conundrum. And climate models, if they look at the CO2 concentration, they look at the planet, and they model this, show that temperature should be increasing. But actually, if you look at the reanalysis data, so if you look at the data from the past 6,000 years, temperatures, especially over the northern hemisphere, have actually somewhat decreased over 6,000 years. And what we present in our paper is that this reduction in temperature, or at least not warming, while the models show there should be warming, could be caused by an increase also in air pollution. Because, and you might find it hard to believe with only a few tens of or hundreds of million people on the planet, but I spend a lot of time in developing countries and around the world, and if you see how people live there, they burn a lot of crops. They burn the land, they burn the grasslands, they burn everything. Because then if you burn the land, then the next season, if the rain comes, there will be fresh grass growing, and then first the wild animals can come there and they eat their grass, and you can hunt the wild animals that come to the fresh grass. And if you have cattle as well, pastoralist farmers, they also burn down the grasslands, which are especially in the semi-wet period, which causes a lot of incomplete combustion, a lot of air pollution. And we see even when the Maori arrived on New Zealand, you can see on the other side of Antarctica, on the other side of the planet, you can see that when they arrived there, that you see soot deposition, so air pollution depositing on West Antarctica, so from all the other side of the southern hemisphere. So
wouldn't it also be land use change, because a third of all the non-ice covered land on Earth is used for meat production, and that didn't start like yesterday. That's been over the last 6,000 years. We've been converting land, and when we burn it, it goes from maybe dark covered
so you have trees
to
grasslands,
grasslands,
to daisies, to indeed
reflect more light.
Yeah, exactly. Yeah, so indeed, that's also what I showed you, the albedo. That's from land use changes. So that's indeed that's included in that. So that air pollution, and that air pollution shows that. So what was this air pollution? That was the biosphere being burned down and incomplete combustion, putting all this air pollution in the atmosphere and changing the landscapes. Less trees, and if you have snow falling on a tree, it will fall down, and that will change the albedo if you take away the tree. So there's a lot of things to consider there. So it's not as easy as saying, okay, you change the land so the albedo increases, but so that
But this is greenhouse gas only in this particular chart. This does not take into account aerosols or land use changes. And you're also showing that we've essentially doubled, to get to the title of this room, we've doubled the greenhouse gas forcing, because it's at 4 watts per square meter.
Yeah.
By the way, we can convert 4 watts per square meter to Hiroshima bombs per year or day or second. That's something that Eliot's adept at doing. What is do you know what 4 watts is, Eliot? What's 1 watt?
That's a different thing than the Earth Energy Imbalance, which
that's true. But this is still the amount of energy equivalent of that particular piece.
I mean, 4 watts would be crazy. Incredible. So I mean, we are being saved by all of the other ways the planet loses the incoming energy. So I think, what are we now, 1.4 watts is the current EEI, somewhere in that range, and it turns out to be about 1.05 million Hiroshimas per day.
It'd be 2.7 million Hiroshima atomic bombs per day would be the energy equivalent of 4, because 0.6 is 400,000 a day. That's the calculation I did with Jim Hansen. So,
I mean, it's so crazy that you you did that calculation and came up with 400,000, and then I heard your interview with Gavin Schmidt where you said, well, that doubled to 800,000, and he's like, no, it didn't. I'm like, yeah, it did. And I mean, now it depends on the time scale. The EEI is subject to so many sort of temporal impacts, from ENSO cycle to, sea ice extent to just cloud cover and all the other things that can, have an impact. And, one of the things that's happening right now that I'm watching really closely, slight different change of topic, is what's going to happen to methane over the next year. Because, if you look back, like
the next year,
I mean, right now it's already starting to take a turn again. But if you look back in 2020, 21, 22, every other article in the mass media and the papers was about this methane explosion, and now we don't even think about it anymore. But it was just, going up like crazy. That was during the La Nina period, and we're right now,
with less solar activity. I think that's also
and one of the mechanisms is that La Nina tends to create a lot of precipitation in equatorial regions that creates anaerobic decay and hence methane emissions. So, we're coming out of the El Nino and into La Nina. So I'm what, because that last spike, and it's funny. It's like I put up this poll on Twitter to see what everybody's concerned about today. And everybody's concerned about AMOC collapse, right? That is the buzz of the day is AMOC. But believe me, 2 years ago, the only thing anybody ever talked about was methane, right? And I mean, not you, of course, because you're all knowledgeable, but in the media, that was the main topic.
Okay.
As I think what's important to note is that the methane concentration in the atmosphere is now higher than it is in the peak of the SSP, I think, for a 5-year scenario. So it's higher than and it's still increasing rapidly. So it should now be decreasing. So if you see the climate models that show, can
I actually show something, the calculation that I've done about methane, because it's just a little bit of a strange, and again, this goes to this whole global warming potential question for methane, which I think is one of the most key questions out there. So let me just see if I can't do a little screen share here and show this. So this is one of the things that I publish every single month. And essentially, this is my favorite picture that nobody understands. This is the first derivative of methane growth, right? So if you actually look at methane, right, methane itself, I think I have it looks like this. All right, this is methane. And if you take the first derivative of this, then, and what I do is I annualize things, take 12 months to smooth things out. And this is what the first derivative looks like. So the methane sort of peaked going up at about 160 parts per billion per year. Now, why can I say it went up by 160 parts per billion when it really only went up 10 or 12 parts per billion? And this is what I do that nobody else does, is I take into account that it has this atmospheric lifetime of 110 months. So if we are at 1900 parts per billion, then on its own, methane is going to decay. A certain fraction of that will decay next year. So the only way to get to 1912 or 1920 or whatever we're at this year is to not just increase that 10 or 12, but to also increase all of the methane that was lost through natural decay over the previous year. And so what I do is I throw in all of the methane that needed to come into the system that would have decayed out, plus the gain in the computation of this derivative. And so this is actually, tells us that methane, sort of the rate of methane growth peaked there in 21 and 22 and everybody was panicking. But that was right in the middle of that La Nina period. All right. We had the El Nino, which tends to lower the rate of methane. And now it's just bottoming out. And I've been watching this very closely. I think we are with all of these greenhouse gases entering the atmosphere, what the climate scientists say is that methane is the thing that's going to save us, right? And so this green line across the bottom that you see right here, this green line, that is the 30% by 2030 Glasgow pledge, right? That is when you actually say we're going to reduce methane 30%, anthropogenic methane 30% by 2030. It means that this line, this derivative has to go down because that's the rate of increase. The rate of increase, we need to only be producing 130 parts per billion a year in new methane.
Quick question is,
yes, sir.
Is that 110 months the most recent lifetime? Because sometime in the last couple of years there was the observation that the decay rate had gone down, which is to say that it stays around longer.
So there's actual all sorts of mechanisms that come to play. So methane decays by oxidation, with a hydroxyl radical. So, for example, if there's a high fire season in the tropics, just Brazil's on fire or parts of Africa are doing slash and burn, then those fires create carbon monoxide, and carbon monoxide preferentially reacts with hydroxyls. It's about 40 times as reactive with hydroxyl as methane is. And so, when you have tropical fires, the tropics is where where over 90% of all methane is oxidized in the tropics, because that's where you get the most solar interacting with, water vapor creating hydroxyls. So yeah, there's all sorts of mechanisms that change the lifetime of methane. So it's not really a half-life per se, and you have, I use half-life because people are familiar with that language, but one of the most important sort of unknown graphs that I would love if somebody could do, but nobody can do it, is to see the change in lifetime of methane, as a function of time. Because if methane is lasting longer in the atmosphere, because we have more fires creating more carbon monoxide, which is, cannibalizing hydroxyls, so that methane is lasting longer in the atmosphere, then all bets are off on methane, all these GWPs for methane. Essentially, methane's upper bound on its lifetime is unlimited. It's only limited by the amount of hydroxyls that are available.
Right.
To oxidize.
And one thing to know is, by the way, if we switch to a green hydrogen economy, hydrogen, when it leaks, is a very powerful, it's not a greenhouse gas on its own. It doesn't like trap heat. It's only because it's H2. You need to have, by the way, 3 atoms so they can vibrate to catch the infrared radiation. But so H2 itself is not a greenhouse gas. Everyone's, oh, that's great. But it interacts with those hydroxyl radicals and eats them up, basically, and leaves less to destroy methane.
Yeah, I mean,
so it turns out it's like I think it was like a 30
it's
times
way
CO2.
up there. Yeah, I mean,
really super powerful indirect
crazy
greenhouse gas.
And I mean, one of the problems that brings up with hydrogen is that hydrogen is such a small molecule, right? And so these pipelines that were created to carry natural gas, methane, or whatever, right? They have tolerances that just, hydrogen just can flow freely out of these pipelines in a way that the larger molecules couldn't. So yeah, I mean, that's a huge problem with the hydrogen economy is cannibalizing hydroxyls, right, and lengthening methane's lifetime.
Pie in the pie in the sky. That's what it's called, right, in English, pie in the sky.
Pie in the sky, yeah.
Yeah.
So at any rate,
pipe dream. Maybe pipe dream is more appropriate here.
Yeah. So I just wanted to make that comment about methane because, when you look at that graph I showed and see exactly where, we are compared to where the Glasgow, pledge was, and yet that is the thing people hold on to as if, the only way to stay below 1.5 is cut methane. And, the problem is that the opposite is happening, right? Methane is actually going up.
But you're saying it's going up at a reduced rate now. That it's actually
for now. It's still going up at a record rate. But
that's true. Yeah, the rate, but the rate it's going up is decreased, but it's still going up.
But
right.
It's still going up very fast. So it was crazy. In a few years ago, it went up by record numbers. A few years. I think 2 or 3 years in a row, and now it's still increasing a lot. And one of the reasons maybe it's not increasing as much as the past years is also because there's more solar activity temporarily because of the increase in solar in the sunspots, and that increases the UV radiation by about 15%. If you have the solar maximum,
that's a good point. That's an excellent point.
And that if you have more UV radiation, you have more hydroxyl And that's the sink. That's the main sink of methane in the atmosphere is hydroxyl. So if you have more UV, there's more hydroxyl, which reduces the amount of methane, but it's still increasing. So I show here is if you have the SSP2 4.5, which is the middle ground scenario from greenhouse gas concentrations. And it's now the concept, if you look at NOAA data, the methane concentration in the atmosphere is now 1930 parts per million, per billion, excuse me. And that's up somewhere up here. So already it's higher than the peak of the SSP 4.5. So that's indeed that adds to the forcing, which adds, of course, why that's one of the reasons why the greenhouse gas concentration is now, the forcing is now 4 watts per square meter, which is equal to what we would have happened if we doubled the CO2 concentration. And again,
but this is like all sources, right? So this would also include methane being released from permafrost. Yeah. So like we're acting as if this is something that we're going to control, but if it gets out of hand and permafrost starts releasing,
it's already out of hand. So this is
it's already out of hand, but I mean
800,000 years, right? 800,000 years. And now we're at 19 so we're close
1.9 ppm.
Yeah, exactly. 1900 parts per billion. So this is really this huge increase, nothing we've seen in the past million years, and it's and that's what adds to the force.
Well, how much of it do you think is? I mean, and by the way, anyone interested, if you want to go way back on the climate chat, I have on YouTube one of our early climate clubhouse interviews with Bob Howarth, who's a methane expert at Cornell. He's the one who said that the leakage from a methane production or from natural gas production is way more than the industry said, and he was born out there. But he also talked about where it came from. Most likely, it was fracking that was increasing it back then. This is an interview quite a while ago. But the question is now, how much of it is man-made? And by man-made, I mean cows, fracking, leakage from pipelines versus feedbacks in the Earth system, permafrost, undersea clathrates.
Not that much yet, and you can look at the carbon isotopes to see that.
Right.
That's going to be in the future, certainly a huge source of methane are going to be these other sources, ESAS and permafrost and melt. The number 2 source, believe it or not, that's non-anthropogenic, it's termites. So, termites turn out to be.
How about rice? Well, rice is man-made, but
yeah. So non-anthropogenic, and if you actually look on CAMs for methane sources, you see that globally the most methane's coming out of Asia, China, and India. That's where we're getting, and it's from rice farming primarily, and other anaerobic decay that's happening in those climates. But yeah, I mean the thing is that there's both a loss of sinks, right, through hydrogen escaping or through the more solar activity or through fires. There's a loss of sinks, and and there's also gains from anthropogenic sources. So this idea that somehow we are going to hit the Glasgow limit, right? This when you hear these limits, it's like the Paris limit, right, of 1.5, right?
Which
is a joke, right? It's a joke.
Yeah.
Everybody says it's a joke. Everybody, nobody will stick. Yeah, but still, it's out there. And the same with methane. It's still this sort of mass, idea that somehow we're going to control methane and that'll buy us time. That's the key to staying under 1.5 is to quick reduction in methane. And that, to Leon's point, the whole thing is that once the solar cycle goes down a bit, once we go out of the El Nino back into a La Nina, right? Once we sort of have these transitions happen, I'm expecting to see methane spike again, possibly to new high growth rates. And
what time period do you think?
Next 3 years or so, right? As soon as
when going down, you think it's going to
Yeah, I think the rate of growth is going to hit a new all-time high again. I mean, along with everything else, it's,
unless we in Netherlands stop with our cattle, and the Chinese stop eating rice, and the Russians fix their oil pipelines, and the Americans stop fracking. I think you're right.
Oh, we'll do all that by next year, I'm sure. We'll get right on that. We'll work on that. Wow. So we covered a lot. Hey, Stacy, join in. Do you have a question or a comment?
Well, first I have
This is, by the way, the highest geek index of any of the climate chat shows so far.
Yes.
So
It's pretty
I have
high.
to-
An
I have to-
HGI.
I have to mug here.
okay, read it to us.
It says, people who think they know everything are a great annoyance to those of us who do.
Oh, I see. Okay.
It's more for you guys than, yeah, I know. Everything is awesome. It's awesome, isn't it? You know?
Yeah.
Oh my God.
Do you actually, was there anything that we spoke? I mean, I'm sure it was very geeky and probably hard for some people to understand. Do you actually have any questions, like to explain a particular thing that we talked about?
Actually, it's more about, this is an award-winning chat. In the YouTube chat was off the hook.
Okay. Okay.
And some of it, it's like, you just, there's no way you could have caught it. But so first of all, as Dan often says, there should be hundreds of thousands, millions watching this, but I don't know, I think we had like 90 some last time I looked. I love this. It's being a fly on the wall while the smart people talk math, live peer review on the internet. Eliot is already thinking about making his next chart, LOL. In 50 years, I would think scientists would have thought of another term for uncertainty when the public understands that word entirely differently. Amen. We're
theory
here,
too.
Yeah, we're here casually talking about the end of life on Earth. What I find somewhat darkly humorous is the general population don't believe climate scientists, but believe politicians. Warming isn't really the problem. It's the result of the changing global systems. I'd actually say it's the idiocy that's the problem. And that there are people that still believe that the more CO2, the better. Plants need it. You know, kind of like Brondo, like
it's plant food.
It's plant food. Yeah. Plants love Brondo. It's what they need.
Who knew things could be two things at the same time, right?
No, it's not possible. It's only one thing. Only one thing possible.
Yeah. I think the western part of the globe generally believes their whole lives will be normal. OMG, just tell me when we all gonna die. But my carbon budget. Or just think about it all like a movie you get to live in, which is seriously, it's like the day of tomorrow toned down a little bit. With hats off to the recent AMOC timeline. And I always had a nostalgia for the 19th century pace of life, and probably we will get to live some of that soon. One person mentioned something that actually is kind of a mathy question. Annette said, hi, I calculated, hopefully I am correct, that 1 liter of gasoline creates 1,000 liters approximately of CO2. And for the regular person, this has a big impact because most don't understand parts per million. And I don't know, because I've been hanging out with you guys long enough that I have a baseline understanding of parts per million. And that's what I've gone with, or tons, you know.
Yeah, I'm not sure what 1 liter of CO2 means.
Yeah.
So, I mean, it's, you know, that's dependent on pressure and you know, yeah, I guess I could do a calculation like that, but maybe somebody
it's almost 9 kilograms. 1 gallon creates 9 kilograms of CO2.
That would be
which is about 20 pounds, roughly 20 pounds of
I guess
CO2.
the other thing for me.
Wait, let's on the gallon. So I had David Archer on long ago, one of my first Clubhouse interviews with a climate scientist, and he did the calculation. What's the cost of a ton of CO2 if you don't discount future damage? And it was $27,000 a ton, and some of the damage continues on for 500,000 years. And he said, and I think I got this right, but don't quote me on this one. I guess I'll just throw it out there, that for every gallon of gasoline you burn, if you took the cumulative warming from that CO2 that you just released over 500,000 years, you'd get one Hiroshima bomb per gallon.
I mean, this is part of the fossil fuel subsidy, right? Is that we're subsidizing over the long run the damage to, and so when you count in the subsidies, that's when it gets into the trillions of dollars a year, effectively in fossil fuel subsidies that are going on.
It's actually trillions without climate impact. It's just cash. Subsidies is over, I just heard 1.4 trillion direct. Last year, because of Ukraine, government started subsidizing gasoline at the pump and diesel and all that stuff and natural gas. And so it was up to like 7 trillion in like
That's the number
subsidies.
I recall. Yeah.
Subsidies. This is not climate damage at
Okay.
all. It's, fossil fuels, when you include all costs, are the most expensive form of energy you could ever imagine using. I mean, it's just crazy expensive. And those external costs, we call them, right? The external costs, which include killing 8 million people a year from just fossil fuel pollution. Again, not climate change, but just the pollution. And now you throw in the climate damage. These are real costs that must be paid. You don't get to not pay them off. So this includes higher insurance costs, uninsured claims. It includes destruction. Look at what happened in Canada. Look, I just actually had my home insurance here in California canceled. And by the way, I already lost a vacation place to a climate fire in the Napa Valley, actually quite a while ago now. So here's someone talking about climate change for 20 years, and people think, well, it's not a real thing. I've actually been impacted very directly. People in Florida are, getting their insurance rates going crazy, getting insurance canceled.
Do you live in the hills?
I live in the hills. I live in the urban wildland interface.
Mm.
And by the way, I don't disagree with the insurance companies.
Oh yeah.
If I were them,
It doesn't math out. Yeah.
I would be doing what they're doing. So I'm just saying that these costs are real. It's not some theoretical cost. Society pays those costs.
Right.
We as individuals or society as a whole, through higher taxes or whatever it might be, to deal with all these catastrophes, and both large and small. And so it's a real thing. This is not like some theoretical thing. Fossil fuels are very, very expensive. If we switch away from them, not only will we decrease mining or extraction by like 99%, because fossil fuel extraction is like 500 times larger than all the minerals that we extract, for example, for renewable energy. And it will save us trillions of dollars, because those real external costs
I think the
will not
subsidies
have to be paid as much.
I think the subsidies are really more about political stability. Because
Well, those are the way there's direct subsidies,
Mhm.
which the government's giving money to fossil fuel companies. Yes. It's still a subsidy if you allow them to create damage that any other company would have to pay for. Like, if you bought you bought something and a crib, and it choked your child, you'd sue the crib company, right, for the damage it caused. Well, this is causing damage all over the world at incredible rates. And by the way, people are trying to start to sue the oil companies. That'll be a very big development. Just like tobacco, it might take a while, but once those suits start to win, that might actually have a positive impact on climate action.
So then it's a double subsidy. But the bottom line is, the reason that they are writing those checks is because, I don't know, I am not a political scientist. I don't know how every government is structured, but I know here the biggest, baddest one of them all, we have elections every 4 years, and we have midterms every 2. And so they want no instability when it comes to economic interests. And so much of that is underpinned by the cost of gasoline. And so,
and Biden released the Strategic Petroleum Reserve to get the price of gasoline down. And it worked, by the way. It worked quite well. And then it dropped, and then they refilled it with cheaper gas. They made a lot of money. The government made a lot of money on that. But so, but by the way, very interesting discussion for that. But that's like a whole separate show.
True.
We were talking about Earth. Well, we were talking, let's get back, a CO2 equivalent. We're
Yes.
talking about climate forcing. By the way, I think, Leon, the chart you were showing with the in and the out and everything, that's like one of the most important charts in the world right now. That no one knows about, but they should, because their lives, their children's lives are impacted by those little yellow and red lines going up and down. And
I think this is if you want to understand climate change, you should start with the forcing agents.
Yeah, but the interesting thing, and we probably don't have time today, but I want to spend more time, because you said some things, and and I kind of knew these things, but I hear them again, and it makes me go, oh yeah. There's the direct forcings from the changes we made to the Earth system. We added greenhouse gases, so that causes this forcing. But then there's the feedbacks, the water vapor, the melting ice, and things like that, and those are included, in something else actually included in your yellow and red lines, right? And where the red line is really just the greenhouse gases. I'm sorry, the top red line. We got to use different colors here. But anyway, this is super important.
So I think I've been asking some around for someone to make a good video of what are forcings, what are feedbacks, what is the energy imbalance. So how do these interact, and how does that result into a temperature increase? I haven't found, and I maybe I should just do it myself, but it would be nice if, for example, if an organization like Koetsgedacht, who are really good at this, could make a video to explain really the basics of what is driving our climate to change, right? And how does this Earth system respond in the short term and in the longer term? And then
we haven't even talked about your paper, Global Warming in the Pipeline, about what happens in the long term, because there was some dramatic information in that paper about getting up to 8°C of warming over with long-term feedbacks included, which is absolutely, civilization is gone at that level. I mean, totally.
Yeah, but I think I call it like the brick wall graph, right? Because we are really running at this wall, this CO2 concentration. And of course, we're now here. This is like 560 parts per million. It is the past 800,000 years, just CO2. And here I show the 560 parts per million CO2 equivalent. I should make this graph showing CO2 equivalent for the past as well. But that would mean, because the methane is lower as well as during the ice ages, that these values would actually be lower. Most of these values you see would be lower because of the CO2 concentration relative to 7050. So the forcing was lower than if you just look at CO2. So that means the CO2 equivalent would be lower than just CO2 concentration relative to 1750.
Yeah. Leon,
so then you see that I think of course the system will like.
Let Eliot get a question in. Go ahead or comment.
I think it's important, to understand that forcing is not the same as temperature and the planet's temperature. That this forcing, 90% of it goes into heating the oceans, so much of it goes into melting ice, so much of it goes into heating the land, and so much of it goes into heating the atmosphere, right? So we have all this forcing, and how that gets distributed, and the changes in distribution that are going to happen as the ocean heats up, and the temperature sinks, like ice melt, start going away, and how that's going to transfer that heating, that 4 watts or the Earth Energy Imbalance from one, more localized like ice melt into global temperature rise, should, for example, we have a blue ocean event, and these are feedbacks that are happening. So I think it's, I think, yes, the 4 watts, the CO2 equivalent is a key number, but also understanding how that's distributed in terms of its heating impact is a key part of this puzzle. That involves multiple feedbacks and tipping points that we're sort of witnessing right now. So any rate, that's just a
That's a
thought.
good point. I wanted to show this as well because this is here's again the greenhouse gas forcing, which is as I showed you is about 3 watts per square meter, minus 3 watts per square meter. This is back in about 20,000 to 25,000 years ago.
Okay.
But if you look at the global surface temperature, there's new estimates showing it's about minus 6 degrees Celsius. But there's indeed the albedo effect, so the changes in, of course, the surface, which is a lot of ice sheets covering North America and Europe up to about where I live. In the Netherlands, the ice sheets too close to where I live. There was an ice sheet ending here, which was about 2 kilometers thick. So and of course it was white and that reflected a lot of sunlight back to space. So you have to take that into account, but you also have to take that into account now because if you have more warming, there will also be less clouds because these clouds will evaporate in a warmer climate. So that all and this forcing, I agree with Eliot that it's really crucial to understand where these forcings are, because if you look at the aerosols, those aerosols were mainly are mainly emitted, of course, over the northern hemisphere. So that's why we've had so much. We've had in our assessment so much warming in this region where most of us live and grow our food in the past 10 years, because there's so much air pollution is being reduced, and that was hiding over the past decades. The preceding decades was hiding much of the warming, especially over the northern hemisphere. And because it was hiding warming over the northern hemisphere, that was also increasing how much heat was flowing from the southern hemisphere northward, especially through the AMOC, through the North Atlantic, through the Atlantic Ocean, right? And if you now decrease the air pollution, you also increase how much heat is accumulating in the northern hemisphere coming from the sun. So there's not a global forcing, there's not a greenhouse gas forcing, because greenhouse gases distribute relatively homogeneously around the planet. But these aerosols, they stay in the atmosphere for a few days and weeks, and they rain out. So that means that if you reduce the forcing, the negative cooling forcing over the northern hemisphere, they will increase how much heat is absorbed over the northern hemisphere, and that will decrease how much energy flows from the south to the north. And that did I show that? Am I showing the graph here? No, I'm not sharing, right?
You're not sharing right now. You had it before.
That AMOC is also crucial to understand, not just from the scary scenario of what will happen to Europe and sea levels rising around Europe and Europe cooling down, but also here this is really an important graph showing that when the AMOC is weaker, this is in sphere drops, this is 1 million cubic meters of water flowing from south to north with a lot of heat, with a lot of energy flowing northward, a lot of zetajoules of heat flowing northward. That when the AMOC was less strong, if you look at the Paleoclimate data, so data from the past, in these periods when the AMOC was weaker, you see that the Earth Energy Imbalance was much stronger. So more heat was accumulating in the system when the AMOC was weaker.
Wow.
And that's also crucial to understand. And it's
I didn't realize that. What is that caused by? Why is that? That's interesting.
Because because less heat is going northward and more northern hemisphere, there are higher temperatures, so you have more outgoing long-wave radiation, and much of that additional heat. So the global temperatures are lower. So the global surface air temperature.
Oh, so we're not radiating as much heat away.
When the AMOC is less strong.
Yeah,
There's more heat, so there's less heat going out, and and there's also more heat, for example, going to the melting of ice. So if you have more heat in the southern hemisphere, there's more sea ice around Antarctica melting, which will reflect less sunlight to space. But also there's more heat going to melting of the ice sheets, which takes a lot of energy. So temperatures might not go up globally on average as much, but who cares, right? Who lives on the global average temperature? No one. So, but the sea levels will rise much faster as well, because there's more ice melting, because there's more heat accumulating in the system faster. So these are all
right. Hansen said there could be
things
10
to take
feet or
into
more
account,
this century.
which are not really there if you just look at the global average forcing or the global average temperature change. So I fully agree with Eliot. It's crucial to take these regional effects into account, which I've been trying to highlight for a few years now, and it's difficult because, but I think it's much more tangible for most people. So I think and it will affect many more people if you have regional forcing changes.
Okay.
If you don't take into account aerosols for the aerosol forcing over Europe, for example, you underestimate summer warming by about 0.5 to 1 degree Celsius. I've shown that before. So you really have to take these regional changes into account. Otherwise, it's a comparison to the statistician.
Hold on, Leon.
Sorry. Eliot has to go, and I have one question for the both of you that I hopefully will be easy, and you can sum it up. Every time I have we have people like you on, I am asking, how much of this could we model? Don't we have enough compute now that we could put in, here are the things that do this, here are the things that do that, and figure out.
These models are so huge, and they take such enormous computing power to run, and they're run every decade or something. I mean, I think, when was the last one run? 2014 or something like that. I mean, it doesn't take into account COVID or Trump or
there's one running now.
Is there? I mean,
yeah,
we definitely. I mean, we're definitely hungry for an update to these things, and so if it was just a question of firing up my PC and running one, I would do it for you. These are huge undertakings.
But it's really important.
So I think
I've got to go, everyone.
Bye, Ellie. Thank you, everyone. By the way, we're coming up on 2 hours, so we're going to skip the audience questions here because I do want to keep it under 2 hours. That probably would trigger a few more people watching later. Leon, thank you so much for coming and sharing all this amazing, mind-blowing information, which, again, I think the geek index is off the charts today, but we'll see how people enjoy that. And we could also spend time in future episodes actually explaining it more in simpler terms for people as well, which I think is a valuable thing we can do here as well. But I'm always learning every time we do this, and I have to process some of this myself. Thanks everyone for coming to the geeky version of Climate Chat, and thanks Stacy as well, and Eli, and everyone who's listening. Leon, thanks so much. By the way, happy birthday coming up, so enjoy that as well. Okay.
Thanks.
And we'll see you all next time.